This is Inventors in Asymmetric Warfare fighting AV-evasion. So my name is Schroeder. I go by the handle Harmjoy. I'm a security researcher and red teamer pen tester for a group called the Adaptive Threat Division for a company called Veris Group LLC. We operate out in Northern Virginia. We do a lot of, like private sector and kind of with government stuff like pen testing, assessments, all those kind of things. I'm a co-founder and one of the active developers of the Veil framework. So, and I ask this every single time I talk now, how many people use the Veil framework on a regular basis? Awesome. Our site is veilframework.com. So I co-wrote Veil-Evasion, which is kind of the flagship tool that generates AV-evading executables, which I'll kind of dive into some of the guts of for this presentation. I wrote Veil Catapult, which is a delivery tool, Veil PowerView, which is a PowerShell situational awareness tool, Veil Pillage, which is a post-exploitation framework that was released at DEF CON, and I also wrote a tool called PowerUp, which is a PowerShell script that helps automate a lot of Windows privilege escalation vectors. I talked at ShmooCon this past year on AV-evasion with the Veil framework. I presented there with Christopher Trunser, who's one of the other main developers. Talked at DEF CON on Pillage, and talked at DerbyCon a few weeks ago with my boss on passing the torch, old school red teaming, new school tactics. So real kind of quick, what I'm going to go over today, I'm going to kind of go over the problem space for antivirus detection and all these types of things. Kind of the initial motivation for Veil-Evasion and some of the ethical issues surrounding it, some of the flack we got for releasing it, just kind of wanted to let you guys know, like we thought very heavily about these things. We weren't just trying to, arm script kiddies or something like that. Then I'll start diving into some of the approaches. And the general idea with, I'm kind of walk through this talk is, we started from not really knowing what we were doing for AV-evasion. We don't claim to have invented most of this stuff or really much of any of it, but for a lot of the obfuscation methods I'm going to go through, I just kind of wanted to walk you guys through our thought process of, okay, this kind of works, this seems more effective, and just kind of trace through the evolution of a lot of the obfuscation methods that are used in Veil-Evasion. And then at the end, I'll cap off with some kind of brief payload analysis for a few of the different classes, a few of the different languages, and show you how really, in our opinion, kind of the static signature detection for executables is pretty worthless now. So the halting problem. I know this is kind of weird and kind of funky if you don't have a computer science background, but essentially, like 70, 80 years ago, Alan Turing proved that it is not possible to decide whether an arbitrary program will eventually halt or whether it runs forever. So like, okay, what does this really matter? What does this mean to me? This is used by a lot of computer scientists to prove whether or not a specific task is impossible. And they'll show that it's called by reduction, to where if you can show that a task will result in solving the halting problem, then that means that task is impossible. So what this is, it's actually kind of a brief little outline of a reduction proof. And the whole point of this is that perfect antivirus detection is impossible. It's an undecidable problem. You cannot have a 100% effective antivirus solution. It's like there's a proof on paper that says you can't do this. So, but even though a perfect approach is impossible, approximations can be made. The reason I'm kind of talking about this briefly is like we know that our task of breaking it is exponentially easier than actually building the appropriate detection. And we're not just sitting here saying, ha ha ha, antivirus is completely worthless. We've been in this problem space for a couple years now, and we know this is a very hard problem. But we still think that there are ways that we can push antivirus vendors to have a bit better detection, a bit better methods, just kind of try to push stuff forward a little bit. So our initial problem, we're pen testers. This is VirusTotal. If you guys don't know what VirusTotal is, just definitely don't submit all your payloads to it all the time, even though people love to do that. We tried to put a disclaimer in Veil-Evasion of like, if you want this to keep working, try not to submit it to VirusTotal. People still do anyways. But this is a stock meterpreter stager. I think this is about a year old or so. The issue is that these stock stagers around 2009 or so started getting picked up by antivirus. And the way the MSF Venom, the EXE generators will work is they'll use these stock templates that they have, which you can change if you want to, and they'll throw like some shellcode in after it's generated and it'll inject it in memory and off you go. So antivirus vendors just wrote static signatures for these kind of stock templates saying, ha ha ha, okay, you're secure now, but Even just changing the templates themselves gets you a lot better AV-evasion. So after this started happening, we kept burning time on limited time engagements. If you have 3 to 5 days for a pen test, you don't want to spend an entire day rolling an AV bypass method. We were never able to not get by antivirus. It was just a matter of time. So in our opinion, for our engagements, if we wanted to demonstrate as much value as we could to a client, saying, oh, okay, we spent this entire day trying to bypass your AV, if we could kind of weaponize that or script it up or automate it, we can spend a lot more time. We can spend that that full day of work actually showing impact to the client and kind of push stuff forward. And also, antivirus evasion is a problem the bad guys have already solved. So we're not releasing, like method ODE or something like that or some crazy stuff. Like all this stuff is public and out there. The fact that it works, it still works extremely well, even though this project's been out for almost 2 years, is kind of sad. But and also, all of our initial efforts when we started researching this stuff 2 years ago drew from previous work. We don't claim to have invented any of this kind of stuff. We didn't invent using Python to inject shellcode. We didn't invent using PowerShell to inject shellcode. We didn't invent, writing pure meterpreter stagers. I'm going to try to cite all the kind of the prior work along the way. So specifically, the first kind of public resource to talk about using Python to inject shellcode, which was kind of the first method we stumbled upon, was a post by Mark Baggett, worked for SANS, saying tips for evading antivirus during pen testing. And in this post, he talks about using a C-types data structure in Python to just kind of do really basic shellcode injection. Dave Kennedy released a tool, PyInjector, in 2012, which is kind of a compiled up version of some of these same types of approaches. And you can run the executable and then a string of shellcode, injects into memory. And we actually ended up drawing mostly from, I know I'm going to mispronounce this, Debashish Mendel's execute shellcode using Python. And this post talks about kind of the standard pattern where you use virtual alloc to allocate a chunk of memory, use create thread to, virtual alloc to create a chunk of memory, use some other methods to move shellcode into that memory, use create thread to kick off execution for all of that, so it just kind of goes, and use wait for single object to wait for that shellcode to finish execution. So our solution, after looking at all this kind of stuff and thinking, okay, Python seems like an effective way that people have been doing this, is we wanted to build something that got around antivirus as easily as professional malware. We didn't have to want to write our own backdoor each time, re-roll a bypass method. And one thing, I'm sure a lot of you guys have done this, like kind of how it was a few years ago, the Python stuff would be great, but you would have to have a Windows VM and use this Pwnstaller or PyDexe, generate your shellcode manually, drop it into the Python thing, like drop it into a Windows VM, compile everything up, like pull the exe back out. If you made one small mistake or something like that or wanted to change the shellcode, you had to like redo that entire process. So it took a little bit. We started thinking there has to be a better way to do this. So we, Christopher Trunser, Michael Wright, and myself, the main developers, we wanted to build a framework that generated payloads in a kind of language and technique agnostic way. I think it was about 1.5 years ago when the project kind of finally hit public for Veil-Evasion. The code base was private for a while beforehand. We debated a lot of these ethical issues for a while, which I'll go over here in a second. Finally decided to open source it. And the big premiere for it was this past year at ShmooCon 2014. It was a presentation called AV-evasion with the Veil framework. I think the slides and like the video and all that stuff are online if you want a little more of a detailed overview of the framework itself and a lot of its capabilities and how it ties into everything. This is kind of the interface. We kind of have a standard interface for most of our Veil tools, but we have payload modules to where you can build these generation modules which generate the source code for whatever language you want. You can write your own custom bypass methods and actually just drop them into the structure. So say you want some cool new Python thing, you could write a module for that, drop it into the tree, the framework will load it up. You can inject shellcode with it, wrapping MSF Venom, new custom shellcode and all this kind of stuff. But it's really nice to where if you don't want to, we still haven't gotten a pull request for any modules because obviously people want to keep their bypass methods kind of close to the chest. But if you want to write your own, you can just drop them in and take advantage of like the C, the Ruby, the Python, all the kind of the compilation stuff and the shellcode generation. We have some posts on developing your own payload modules and all that kind of stuff up on our site, the veil-framework.com. So the ethical issues. The disclosure debate has been going on for a long time. It's kind of really centered on exploit disclosure. But our view, and most of the people I talk to seem to agree, is that pen testers are at least 5 years behind the professional malware community, and I'm sure even further behind, nation-state communities. But again, like I mentioned, this is a problem the bad guys have already solved, and they've done it better than we have. So if we're trying to demonstrate value to clients and saying, if you're trying to simulate what a bad guy is actually doing, you need a method to at least simulate some of this type of stuff to get, bypassing these types of defenses. So antivirus, it's pretty much a joke to professional malware guys. I think one of the last point-of-sale malware samples didn't get flagged by a single antivirus engine. This isn't really an issue for people that are paid to do this. However, when we released this tool, these are quotes from the original Reddit thread where a lot of people were not happy. I think one of the quotes was, surely this will just result in 21 new signatures for all major AVs and we're back to square one. That hasn't been the case. And isn't our field meant to be working towards increasing security rather than handing out fully functioning weapons? So I think that's a little ridiculous if, just wrapping public Python shellcode injection methods is, handing out cyber weapons, then whatever. But one of the quotes we did like was, someone pointed out, and kind of we agree with the sentiment, is that anything that helps to expose how ineffective antivirus is at stopping even a minimally sophisticated attacker is really a good thing. And that's kind of our point. Like, bad guys aren't dropping, 4 megabyte like Pwnstaller rat malware, but we can actually at least simulate some of these actions on a limited time frame engagement using some of these techniques. These are our favorite quotes from Twitter. So the main thing, this is during the ShmooCon presentation, but the main thing that bothers him about the Veil framework is that new pen testers will never know what it was like to do all this manually. So like I talked about of having to roll your own stuff or writing your own C stager and all those types of things. We wrapped all that stuff up and tried to obfuscate as much as we could, which I'll go through. And then Script Chunky, responded back in my day, we had to obfuscate bits by hand uphill both ways. So just shaking the fist. We just made it too easy, I guess. But like I mentioned, so we kind of started with Python-based shellcode injection techniques. We soon started kind of branching into other languages because we wanted to make it, like I mentioned, kind of language and technique agnostic. So if you have your payloads pretty similar each time, kind of a stock template, this is the problem that Metasploit started running into, to where it's pretty easy for antivirus to just do, a stock kind of static string signature for it. So we started thinking, okay, how do we start kind of just basic obfuscation for this stuff? So all right, let's just randomize every single variable, every single method. Just go through it and say anything that can be randomized, let's go ahead and do that. This is very simple. This, obviously is nothing crazy. The sad thing is this is still really, really, really effective, much more so than it should be or you think it would be against a lot of antivirus vendors. So this is kind of an example of what one of the Python payloads will look like now. If you're extracting this out, anyone that knows how to RE or actually do manual reversing for this stuff or malware analysis is going to be able to figure out what this does. The idea is not to, stymie advanced malware reversers because we're not going to be able to do that. But we wanted to have an automated solution that tries to scan this stuff. We wanted to at least throw a couple wrenches into that automated detection process. So sticking with the Python stuff, our next idea was, okay, how far can we take all that Python obfuscation? And what if vendors still find a way to trigger on some small components of the Python script sources? So we looked at the Hyperion project, which is a kind of PE crypter. It'll take any executable, do a little stub, encrypts it with the random AES key, and then actually brute forces the key in memory. So our approach, kind of similar, was you take this little kind of crypter, feed it any Python import file, and it'll do a random AES key, base64 it, and roll it all up in this little kind of exec wrapper. So you go from something that looks like this, you see all the shellcode up there and all the stuff down there. You can see the create thread, the wait for object, the virtual alloc and all that kind of stuff. So maybe they're doing some signatures for that series of calls or something like that. That's what it'll look like now. And now it's really hard to read really small text, but you basically import a couple things. It just says exec. and it's this giant base64 encoded thing. This will, on base64, decrypt all of this in memory, like decrypt the entire script to inject shellcode, and then execute that in line. So every single time you generate this, even if it's the exact same payload input file, this entire thing will change. So we're like, okay, that's about, seems like kind of about as much randomization as we could get for Python at least. We're like, okay, thinking along these lines too, we just started kind of brainstorming. Like, what if for the shellcode injection, like AVs are actually triggering on some of the raw shellcode itself? Started researching some stuff, and the way that meterpreter stagers work really aren't that complicated. Raphael Mudge, who's actually out there at the Cobalt Strike table, had a couple posts that I found. It wasn't even posted at the time. It was some like email threads on the Metasploit mailing list back and forth with Egypt. So in that, he was kind of working out, like, how do meterpreter loaders work? And he actually put a post up, I think last year. This is after we kind of devved our own stuff. But he has that blog.strategic cyber, the stage payloads, what pen testers should know. He goes through kind of some proof of concept code and like really tells you exactly how this stuff works. So before, to me, it was kind of a little bit of black magic. I was like, okay, under the hood, it does something and loads it all up. But again, it's actually pretty simple. For the reverse TCP stager, the shellcode will open up a TCP connection back to your MSF console, your meterpreter handler. The handler will spit back 4 bytes, which indicates the size of the DLL it's about to give you. Right after that, it pushes out the DLL itself. So meterpreter is a reflectively injectable DLL, which means that you can spit this back out, and an agent or like the shellcode of the loader can load it all in memory without touching disk, and then you can migrate around and do all your fun stuff. Then the shellcode will push the socket number into EDI. And the reason it does this is, you kind of have your data channel where you're staging the DLL, and then you want to have communications with the handler itself. So this basically saves off the socket number and uses that same channel for communications. So you open up a socket to download everything, and you can keep using that same connection to do all your like C2. It does like a SSL negotiation, I believe, underneath the hood, and then you do all your commands and stuff. And execution is past the DLL just like you would with shellcode injection. You do the void pointer casting, the virtual alloc pattern I talked about, all those kind of things. So the reverse HTTP handler or HTTPS handler are even easier. You don't have to worry about the socket number because it's asynchronous. You just connect to the handler, you get a big blob of data, which is a DLL, and you inject that into memory, and then it just takes care of its execution. So we started writing these pure stagers for the framework. It's kind of an interesting approach, and then once we kind of figured out what those stagers were, we started translating them into different languages. So we have several stagers available in the framework right now. We reverse TCP, HTTP, and HTTPS all in Python. And again, because this is all modular, you can use like that little Crypter, you can use any of the options. We have things for Python to have like kill dates, additional obfuscation, your shellcode injection methods. We can also do like heap alloc for injection instead of virtual alloc, things like that. We have a few versions of some C obfuscated ones, and I'll go over the C obfuscation in a little more depth here in just a bit. But we have reverse TCP and reverse HTTP, and we also have service versions of those. What's nice with those is you can actually ps-exec with them. So they respond to the service control handler. You can generate these with Veil-Evasion and then plug them into ps-exec for Metasploit and just have them work. So these have been pretty effective, we found. It's a lot harder to write malware in C because it's easier for AV vendors to detect it. Sorry, it's a lot harder to write really good evasive malware in C as far as all this obfuscation goes, because Python or any other kind of interpreted language, you have standard ways that it's all packaged up, and then you have the only malicious part is like the little script that's kind of compressed up. So it's a little easier to write stuff for that, we feel, which is why that's been a lot more effective for 2 or 3 years, because AV vendors can't just flag on the little loader at the front, because that would block a lot of legitimate projects as well. So we did some reasonable obfuscation for the C stuff, and then did the service versions. There's also actually some Cortana scripts that will let you plug Veil-Evasion into Armitage or Cobalt Strike, kind of generate this stuff transparently in the background, so every time you ps-exec, it'll choose one of the C service ones, like substitute it in and do all that. So this kind of helped our workflow. So also, we branched into C#. And something that I didn't mention, all the languages that we have in the framework, we want to compile on Kali Linux, but work on Windows boxes. So we don't want to have multiple VMs and do all those kind of things. So everything we've released will compile up a Windows exe all on Kali, kind of as a monolithic attack platform, and then you can just drop them and they'll run on Windows. So with the Python stuff, we actually run Pwnstaller under Wine on Kali. The setup will install all this stuff transparently underneath the hood. You don't have to configure everything. You don't have to worry about it. You just point and click. The C stuff uses Min32 or MinGW32 to compile everything up. The C# stuff uses Mono. Now, people have kind of yelled at us or saying that we have a huge number of dependencies for the project, which is true. But if you want to compile .NET code on Kali and have it run on Windows, you have to use Mono. That's the only option. Unfortunately, it's like 700 megs of dependencies for Kali or something like that, but is the only option. We have some PowerShell stuff, also the shellcode injectors, as well as these pure stagers. And we now have Ruby, which I'll go over here a little bit more. That was released about a few weeks ago, about a month ago. Yes?
Does compiling on Kali, compiling a Windows binary, leave any artifacts that if a normal vendor that compiles on a Windows box?
For the interpreted languages, I don't believe so, because, and I'll go into some of the details on how, say, Pwnstaller works. But basically all it does is it has like a little static loader at the front, and then it makes kind of a big kind of semi-compressed, something kind of like a zip that it tacks onto the end. So because of that, you're not really compiling anything, you're just kind of compressing it and making a self-extracting exe. So like Python, Ruby, and that type of stuff, no. The C stuff, yeah, you can tell that it was compiled with like MinGW32. And we've seen there was one vendor that started flagging some things or using that as an indicator. But it's not 100% or anything like that. And we always have questions from people saying like, oh, have you looked into getting around this vendor? Have you seen that? Like, there are a lot of AV vendors out there. We don't have the kind of like the time or resources to constantly test and fight against every single one of them. That's why our approach is we always want to do a ton of methods. The idea is if you're going up against a target and you know what their AV is, then you can just clone it off and like see what works. Cool. So, like I mentioned, for some of the C stuff, variable obfuscation really doesn't do as much for a properly compiled language. It can help for an interpreted language. It's a little harder for C. So we're like, okay, how can we go about this, really basic obfuscation? So again, this is nothing crazy. Malware's been doing this for a long time. I did not invent obfuscating C code, but our kind of slightly more advanced or intensive obfuscation for C involves kind of our interpretation of a method knot. So the idea is you want a lot of methods interspersed throughout the code that don't do anything functional for the program. They just kind of waste space and complicate the call tree. So you have a lot of these methods, you kind of nest all of them. Our approach, I think I did this in about an afternoon, was malloc a whole lot of C strings and have a whole bunch of nested string processing functions, and then spit these out in randomized places throughout the code, like in between the virtual alloc and in between the create thread. A lot of times AV vendors like to say, okay, you're doing these two calls right next to each other, allocating memory and then moving data into it and then creating a thread. A lot of stagers and loaders from malware do that. So if you intersperse kind of new data and processing in between those specific calls, that seems to be really effective. So this is what all the C methods, or the C stagers and stuff, in Veil actually do right now. And again, you want to muck up the dynamic analysis a bit without affecting the actual execution of the program. Anyone that's a reverser is going to be able to figure out what it's doing. Again, that's not our goal to stymie all the actual reversers. But if we sufficiently complicate the call tree of the program, that seems reasonably effective against combating a lot of these antivirus vendors. Again, this is a basic version of what malware's been doing this for a long time. It's still really, really effective. And like I mentioned, we had a bunch of randomized string processing stuff, malloc all the strings, intersperse and randomized functions throughout the actual code. That's kind of what it looks like. I know it's really kind of small again, but we have all of our randomized string stuff, and we intersperse that all throughout. Again, this is an open source project. AV vendors, or you guys, if you're curious, can go look at the code and see exactly what's happening. Whenever we generate an executable, we also always give you the source file and the compiled version of the file. And I think Christopher Trunser actually just put up a post on our site recently about how to actually extract the Python source file from the exe so you can verify it against the source if you don't trust us. We promise we're not backdooring the backdoors or whatever, but some people are paranoid. No. So the next thought was, okay, if some AV vendors, what happens if they're actually triggering on that little Pwnstaller loader? Like I mentioned, it's this little exe. It's static, so every Pwnstaller binary is going to have the same little loader. It creates this C archive data type. It compresses a minimal Python environment into it, sticks at the end of that exe. So when it runs, it extracts that all to disk temporarily, invokes your script file, and kind of off you go. So we started thinking, okay, what if we made an obfuscated version of the Pwnstaller loader? So built that last year, presented at BSides Boston this past spring. It's called Pwnstaller. The source code's been integrated into Veil-Evasion. So it's an option whenever you do Python. You can say Pwnstaller, which is the default, or this Pwnstaller option, which will generate completely randomized source files for the little loader at the front. Generate all that stuff, compile everything up, move it in transparently. So end result is every single time that little obfuscated loader in the Pwnstaller binary is going to be as randomized as we felt we could reasonably make it. And that was integrated into all the Python payloads this past May. So again, obfuscated code, sorry, I'm repeating myself, I guess, associated with the Pwnstaller launcher generated. MinGW32 is used to compile everything. Again, all on Kali. It's copied in, a randomized Windows icon is chosen, all that kind of stuff. There's a blog post on my blog that kind of goes into some more detail about the specifics of that if you're interested, or the BSides Boston presentation. So the next thing, one of the things we realized was any language you have that has a foreign function interface and or has access to a foreign function interface, you can use to inject shellcode or write meterpreter stagers. And it'd be really nice, okay, we want all this stuff to work on Kali, just like we mentioned. So we had C with obfuscation, C# with .NET, and Mono, PowerShell is great. We started looking into Ruby, and it does have a foreign function interface, 132 API, so this little gem. It means we can, write our pure stagers. And Ruby also kind of has an analog of Pwnstaller called OCRA, which is one-click Ruby application. And nicely, we were able to get all this running on Kali. So just like all the little Python injection stuff, there's everything equivalent for Ruby at this point. This is a little stock template for Ruby shellcode injection. It's only a handful of lines. You kind of declare the functions and do that same pattern for, there's your shellcode, you have your virtual alloc, your move memory, your create thread, your single object. And here, so in Veil-Evasion, there's a couple of Ruby payloads now. There's a shellcode injector and a pure verse TCP stager. It'll compile it all up in the background, spit out the exe that works on Windows. Again, you don't have to set anything up. You run the setup file, it installs all the dependencies, it does everything under wine, does all that. About a month ago or so, these were released, the shellcode flat, the basic kind of shellcode injection is how we separate it. We go by language, technique, and then specific approach. The Ruby shellcode inject flat, Ruby meterpreter versus TCP, everything compiled to a self-extracting exe. So this is pretty new. We think it's neat. I hadn't seen, there might be some public stuff out there. We hadn't seen a lot of resources on Ruby stuff at the moment. So the other thing we released last month was, kind of this idea for a .NET kind of Crypter. Because C# and VB code is compiled, not interpreted, you can't really build a little dynamic obfuscator like what we did for Python. But .NET has this really interesting feature called reflection. And this is kind of quoting from the MSDN stuff. You can use reflection to create type instances at runtime and to invoke and access them. Basically what this means is you can kind of manipulate components of certain structures and things like that in memory, in real time in a C# program or a .NET program. The end result is if you have a byte array of raw bytes of a .NET binary, so it can be VB, it can be C# or anything, you can run that entire thing, that executable, you can run that all in memory with 3 lines of .NET using reflection. So it doesn't matter how you get these bytes to that byte array. You can download it from a third party like a dropper. We have an option to where it obfuscates it in a base 64 string in memory. So after you decode that and you get that little array of bytes, you just say assembly load. You set the entry point to be the beginning of it, and then you just do this invoke, and it just starts running. So this is kind of like reflective DLL injection, but it works for any .NET compiled binary. So we released this thing called a crypter called ARIA, which into the framework, it's an option for all the C# payloads now, to where it'll read in all the bytes, or so a payload binary, a regular one for C# or whatnot is generated. It compiles it up, and then it reads in all the raw bytes, base64 encodes everything, does a random substitution cipher on it, and then builds a little launcher that decodes the raw data, injects it all into memory using reflection. So that's kind of just a little overhead up there. Then we have, all that kind of randomized string and everything like that. That's the actual executable that injects all your shellcode. Again, as a proof of concept, you can have this kind of obfuscated in memory. It's really easy. You can do a couple lines, just a couple lines to say, download this blob from, a web server and just inject it. So you can essentially have like a stage 1 loader in .NET in like 5 or 6 lines or something like that. So this is actually something that bad guys actually do. So I think one of the AP, it might have been Putter Panda, I think, did some kind of like stage 1 loading with reflection .NET stuff. And then they had their kind of stage 2 malware stuff loaded up purely in .NET and kind of went in. So it's we're trying to, again, simulate that kind of stuff. We're not claiming we did it better than any of those guys, but kind of approximate some of these techniques. Cool. So I'm going to go over a little bit of the payload analysis of a couple of the families and then wrap up and take some questions. So SSDeep is a very kind of basic static analysis tool for malware. It's a fuzzy hashing comparison tool. So the other word for this, the nice official word, is context triggered piecewise hashes. So it does this thing from the man page saying it can match inputs that have homologies. So it's this biology term. It's a fancy way of saying, can we measure the degree of shared ancestry between 2 bits of data? So if you have 2 executables, this will kind of it'll break it all up into components, do like hashes of a lot of the small components, and then do a comparison and give you a score, saying how much of these code bases are similar from like a static kind of standpoint. I'm not a reverser. I asked some like kind of reversing friends saying like, is there a really easy tool I can use to just compare some of these malware families? And they said for triage, a lot of times they'll use this in that kind of stage 1 triage, spit a whole bunch of samples through it and kind of say, okay, if it scores at least like an 85 or a 90, then they're probably kind of the same payload family. They have most of the same kind of ancestral code base. So what I did was, for a couple of these families, I generated 1,000 samples of each and then did a run of comparisons. So it did 1,000 choose 2. It compared every single possible pair of the entire thing. Then I ran some stats on some of the scores and everything. Like the Python meterpreter versus TCP. Of those 1,000 samples, the 1,000 choose 2 gave you almost 500,000 possible pairings. And only 1/3 of them match at a score of 75 or better. Only 66 of them, or 0.1%, scored at 90 or better out of 100. And from my friend's kind of like basic information he gave me, saying like, okay, only 0.01% of these kind of count as the same malware family. Even though they're generated using the same kind of technique, this didn't use the Pytherian stuff or anything like that. It didn't use the obfuscated loader. You still get kind of pretty good variation of a lot of it. The average pairs-wise score was 74. And a lot of these really kind of scored off to where they weren't similar at all. So these techniques give you kind of like a really nice kind of spread to where like these aren't the same kind of payload family. Where this shows kind of a graph of all the SSD matches for the Python interpreter TCP. You see it kind of spikes up around 74, but it trails off pretty fast. So there's reasonable variation. The C, like I said, it gets a little more difficult for the obfuscation. We did the same 1,000 samples, same about 500,000 possible pairings. About half of them scored at 25 or better. So about half of them scored as completely dissimilar, which is pretty awesome. And only 0.5% scored at 90 or better. The average pairwise score was 37. So very few of these, just kind of like the Python stuff, scored as a similar malware family, but there was a lot wider variation than the Python stuff. Like there's no super specific spike. There's a lot more kind of all over the place. It kind of fell off after it hit. I think the threshold for any score at all is like 35 or something like that. But. So this is why this is going to be a lot better to use this kind of your stock PSExec stuff than just using the same template. This is a little harder. It's not impossible. It's a little harder to write just a static signature for it. Then doing the C# stuff with the little .NET Crypter, only about 5 pairings matched at 25 or better. None scored at 90 or better. So this variation, I didn't even graph this because the variation was, there was like 1 data point, so it was just completely off the map. So none of these scored as a similar malware family based on SSD. If a reverser started looking at this, they would see like, okay, these are actually very similar, but again, that kind of first automatic triage type stuff, that's what we're kind of trying to get by. So in the recap, we started this research out of necessity, but then we kind of continued out of curiosity. We, again, a couple years ago, we knew absolutely nothing about any of this stuff. We were able to build some really effective approaches very, very quickly. This is not rocket science. This stuff isn't that hard, except beating up AV vendors isn't extremely difficult. But there's still ways to stop us. We went over this in the ShmooCon presentation. Proper behavioral analysis is really the way to go. Some vendors have started doing this to where you're like, okay, let's hook the virtual alloc calls, kind of at least detect to start that virtual alloc pattern. That's a pretty effective thing. There's a project called Ambush IPS released by ScriptJunkie, which is a very granular kind of host-based IPS system. You can write rules that say, if you do this call, then this call, and this call with these types of arguments, then flag or block. So you can write rules that block all meterpreter loaders or things like that. Again, the problem is, though, we don't want vendors to just stop pen testing tools. You want them to actually stop real malware because they're just trying to simulate this stuff. One thing we've seen that's been really effective that a couple of vendors do is kind of crowdsourcing the reputation of the EXEs. So if they've never seen an executable before and it hits disk, they say, okay, we don't know necessarily if this is good or bad, so we'll pop up to the user and ask them if they actually want to run it. Or they'll apply much more stringent kind of heuristics to it if they've never seen that sample before. So that's really kind of flummoxed us a bit, but luckily PowerShell gets by all that stuff, so you don't have to worry about it. And it's still kind of interesting. That's at least, they're thinking in a different way besides just static signatures, so that's really a really awesome approach that we would encourage the vendors to kind of move towards. And then, yeah, that's our hashtag, AV-evasion. So that's it. I know it was a little short. If you guys have any questions, always feel free. I'm on Twitter or my email. The site, we try to do a lot of blog posts, pretty much kind of diving into technical information or releases for any of the modules and things like that. The things I didn't mention is we actually have a standard kind of release cycle we do. So it's called V-Day, kind of modeling after Patch Tuesday, to where the 15th of every month for the last year or last 13, 14 months, we've released at least one new module, our payload family. So this past month was the Ruby stuff. We actually are a couple days late for this month, but it's going to be the Ruby reverse HTTP and HTTPS stagers. Next month we got some, we have enough research to where at least for a few months out, we always try to stack stuff up. So we've got, I think, probably at least 9 more months of releases if we didn't do any more research at this point. So again, we didn't want to just kind of drop it all at once. We're just trying to, as we figure out stuff and kind of move ahead, we want to keep releasing it to let people know this project is alive, we're still doing this, we still think it's interesting. So, and then the GitHub is Veil Framework. That has all the separate tools underneath it. Veil-Evasion is kind of the main tool. We have a super project called Veil that we recommend you clone that down and run the setup, and that'll run everything for the standard configuration for the additional tools like pillage. And actually, this fall, or pretty soon, we're going to start rewriting the entire code base from scratch. So all the tools will actually work together. It won't be, the setups won't stomp on each other and everything anymore. But, all right. So yeah, it's going to be a complete rewrite for kind of like a 3.0 release that's going to be sometime in the spring. So. And we also just released our own kind of a port of MSF Venom into Python. So now we don't have to wrap, we're basically independent of Metasploit now, or we don't need it as a dependency if you don't want it. So you don't have to wait for the whole Metasploit stuff to like spin up. It can just be like instant shellcode generation. So, cool. Any questions? Yes?
Do you have to worry about your entropy scores at all?
We haven't looked as much into that yet because we haven't had to. We know some approaches or some AV vendors are saying like, okay, if this section has a whole lot of randomness, that might be suspicious or might be a kind of packer or something like that. We haven't looked into it yet because we just haven't had to. But that's something we'll probably start looking into in the next few months. But maybe a way to, instead of making it look completely random, try to mask it as like normal looking text or different kind of encoding method or something like that. Yes.
How much does this look like commercial IP obfuscation protection techniques?
Honestly, I don't really know. I haven't looked at any of the commercial solutions for the obfuscators and packers outside of the kind of the standard open source ones like UPX or whatever. The thing is with us at least, like each language is it's very, very different. It's kind of a different approach. So at some point, we'll probably look into some of the commercial things, but this has been effective enough to where we just haven't had to look at the commercial stuff. But it's something to definitely look into. Yes. All right. Sorry, could you repeat the question? Yeah, I talked to a couple of friends who are reversers. There's a couple other techniques for shellcode injection that we're planning on introducing and things like that. But yeah, our shop doesn't really do reversing ourselves, so we don't have a huge amount of insight outside of kind of what's publicly out there in reports. Yep.
Is there any plans for 64-bit?
We've been asked about that a lot. That was one of the biggest questions we got at DEF CON, so we actually, as soon as I stop traveling nonstop, I'm going to try to actually start looking into it. But we've got a few new people that come on board, and once we start doing the framework rewrite from the ground up, we've kind of pushed a couple of the feature requests to be like, okay, we're going to reset everything anyways. So we're definitely going to try to look into how to programmatically integrate 64-bit stuff and compile it, especially because things with patch guard and all that make it real. 64-bit can be really, really effective in evasion stuff. So that's for on-disk evasion. That's going to be kind of one of the next iterations for it. So cool. Unless anyone has any other questions, that's it. Thank you.